present your entire screen. Screen 1, there we go. Okay. Let's do that. All right, so as a little review, we talked about force, all right? We talked about force. Any interaction that when unopposed will change the motion, all right? So we know what force is, all right? The only thing that can cause an object to accelerate is force, okay? That makes sense, right? I went over this on Friday. Okay. Just some background definitions of force. All right. Any interaction when opposed will change the motion of an object. All right. So we talked about Newton's first law. All right. You don't have to write it down if you know it. But an object at rest stays at rest. An object in motion stays in motion. Right? Right? Unless an outside force acts upon it. All right? And that's where we talk about the law of inertia. Okay? The law of inertia, the tendency to resist a change in motion. All right? The tendency to resist a change in motion. All objects want to keep doing what they're doing. Okay? Sound good? Wonder if this speaker actually picks up what I'm saying pretty well. Because that speaker is supposed to be hooked up to the projector, which is hooked up to my computer. I guess we'll find out. We'll find out. Okay? Now, when I showed you guys some videos, or I showed you the astronaut video, right? All right, so we're going to skip that. All right? Astronaut? Again. The 5 experiments? Yeah. Oh, yeah. All right. So, if a rocket ship is in deep space and it turns off its engine, anybody seen the movie Martian? Yes. Great movie. Mind blowing. The book's even better. Just saying. Yeah, beautiful. Concept question 1. All right. So, if a rocket ship is in deep space and turns off its engine, will it slow down and eventually stop? Stop immediately, turn right. Hopefully, you don't guess that. And move with a constant velocity. D. Right? Move with constant velocity. Right? You're in outer space. There's no force really acting on you in a vacuum. All right? D is the correct answer. Okay? Concept question 2. Explain when using Newton's first law, why seatbelts should be used. Yeah.
Because you're still moving, even if, like, say, if you got in a crash, you would still be going, like, say, 50 miles an hour. So you need the seatbelts to stop you.
Absolutely. Absolutely. All right. Now, even more trickier. Explain using Newton's first law how you can get away from a moose if it's charging at you.
Sharp turn.
Sharp turns. Why?
Because it's in motion in a straight line, and so it's going to keep going straight unless it tries really hard to turn.
You're exactly right. You're exactly right. Okay.
Or you can just stare at it and, like, will it to stop.
That's a great idea, too. It's a great idea.
We're talking about force, aren't we?
Second one, take turns, sharp turns. Kind of like, because a moose has a lot of mass, and if it's running full speed this way, it's going to be hard for the inertia wants the moose to keep moving this way. So if it has to turn, it has to slow down first, and then turn. All right? That's Newton's first law. Object in motion stays in motion. Object at rest stays at rest. We feel good on that one?
Yeah.
All right, second law. Force is equal to mass times acceleration. That's literally the second law. All right? Force is equal to mass times acceleration. Okay.
What's the unit for force?
Newton.
Imagine that.
It's pretty clever.
I wonder why.
I don't know. I always wonder that myself. Yeah.
What is the units for mass and acceleration?
Really?
Yeah, because there's many units you could use.
Mass, we're going to be using grams, acceleration meters per second squared.
I've never met the guy, but Isaac Newton seems like a really humble man.
He does, you know. He's like, hey, I'm just going to put my name on these 3 laws, name the entire unit of force after
To
myself.
be fair, he did come up with all this.
He did.
He didn't come up with calculus.
Okay.
Yeah, Isaac Newton invented
So-
gravity, so he did some
If you push a heavy object and then push a light object with the same force, what will happen to the light object? It'll go faster. Right? You'll have a more acceleration. Right? If you push an object with a large amount of force and push the same object with a less amount of force, the object that experienced less force will
Slower.
If you have a big guy, right? If you push an object with a large amount of force, right? And then you push the same object, DJ. And then you push something with a little amount of force. The object that experienced less force will, what will that do?
move less.
Move less. Right? It'll move less. Okay. All right. And then finally, Newton's third law. Newton's third. All right. For every action, there is an equal and opposite reaction. All right. Whenever one object exerts a force on a second, the second object exerts a
Excuse interruption. Graham Garwood, would you come to the attendance office, please?
an equal force. There's no such thing as a lone force. They always come in pairs. Aww. How cute. Yes.
Can I write a question on the board?
Can you write a question on the board?
Yes.
What?
Like,
He wants to write a question.
literally write a question on the board. Can you write it on your paper?
That's possible.
All right.
Well, now I want to know the question.
All right. Newton's third law. All right. Now what we're going to do, we're going to watch. Oh, man. All right. What force is allowing the tug of athletes to win? Tug of war athletes. Now, anybody seen professional tug of war?
Yes.
It is awesome. Okay.
It's indoor champ. What about the X door?
Well, this is only the 560 kilo, man.
Oh,
Yeah, 560. I have no idea.
It has to be. Yes, it is. They're using their legs.
So what force are they using? They started right there. Yeah. This seems like your coach is behind us. Their arms are huge. Look at that.
You would think that their legs.
They got
More legs. Yeah, it's more legs. The first guy's chest is popping out.
Yeah.
You're like, wow.
They're like, all right, we're taking a break.
See them all go.
Someone brings in a rope. Uh-oh.
Oh, no.
Uh-oh. They're sitting down. Uh-oh. Oh.
I think it's, I have to call.
They got back up. Is this guy even falling back there?
Looks like he's standing straight up.
This just seems like whoever's legs get tired.
Oh yeah, they're about to lose.
Yeah.
Game over. All right. What force are they using? Gravity. Wait, so gravity's pulling the rope?
To the side, yeah.
Theoretically. All right. So gravity's pulling it down, right? Gravity's straight down. But when the people are closer to Earth, when they're falling back, the gravity is pulling them down, which down makes them move back.
So is that one?
Gotta go
Yeah.
down.
Really?
But aren't they like also pushing with their feet? And like
Yeah, friction. You put friction, that's fine. All right. Now you can say you've seen National Tug of Wars. You guys want to see how to set up a Christmas tree?
Yes, please.
I'm just kidding. I'm just kidding.
You can do it.
Maybe at the end of class time, you know? All right. All right, so we'll get to that here in a second. All right, let's do a practice problem. All right, 3 people push on a boat that is 752 kilograms. The boat moves next to a deck. Each of the people push on the boat with 80.5 newtons of force parallel to the deck. Did I get my unit wrong? It might be kilograms. I could be wrong. We do use kilograms. I was wrong. You were, yeah, we're going to use kilograms. All right, we're using kilograms. All right, so kilograms is mass. Okay, so if we look at this, the boat floats next to a deck. Each of the people push the boat with 80.5 newtons of force parallel the dock. Okay, what is the acceleration of the boat if they all push in the eastern direction? Okay. So if we do this, all right, 3 people push with 80.5 newtons of force. All right. 3 people push with 80.5 newtons of force. All right, so that's going to be 241.5 newtons. All right, and it equals, all right, the mass. All right, 3 people push on the boat. The mass of the boat is 752 kilograms times acceleration. All right, so what would the acceleration be? Probably 0.4, 0.3?
3, 2, 1.
3, 2, 1.
Yeah.
Meters per second squared. 3, 2, 1 meters per second squared. Okay. What is the magnitude and direction of the boat's acceleration if 2 people push in the west direction? All right, so now I have 2 people going in the west direction, 1 person pushing in the east. Okay. Yeah.
It would be 0.107 meters per second.
All right. So one of the people would cancel the other person out, right? So what we have is a 80.5 Newton man pushing west. All right. And the boat stays the same, 752 kilograms times acceleration. And what did you get?
0.107 0.107.
0.107 meters per second. What direction?
West.
Oh. Oh, wait, no.
Couldn't you just have put negative?
Yes, definitely. If you put negative, you're done. All right, if you put negative 0.107. If all people push in the same direction for 2 seconds, what is the speed of the boat? Oh, we're applying past chapters. Okay. If all people push in the same direction, all right, let's just say they're going east. Okay.
So we know acceleration.
We do know the acceleration if they're all pushing in the same direction.
We have time.
We do have time.
You know, so we can just do the first one. Final velocity equals initial velocity plus AT.
Or,
Because we know the initial velocity is.
or we could just
All right, we can
multiply A times T.
I guess so. That would make a lot of sense. That would make a lot of sense. Hey, I'm not the brightest.
Okay, A times T.
Let's see the
So-
Lewis Turner.
0.6, 0.6 meters per second. Does that kind of make sense? Okay. So what you guys are going to be doing? What you guys are going to be doing here is
Go video.
not the Go video.
Is that going to be a recurring theme?
I feel like the Christmas tree video.
You guys want to know something? Which kind of throwing me off my game because I thought it was this class. There's 6.
Six what?
6 cows plus Julian. That's 6 over there. I thought it was this class, but I'm wrong. I might be wrong. Yeah. No, I didn't. That's 6 over there. I don't know yet.
Wait, I'm confused.
I'm thinking second now. I thought it was this. All right.
You can put a security camera in here.
Because you guys are sneaky.
I can see why
You guys are sneaky. I got my.
Fine class, I can understand why you think it's us.
All right.
I mean, we're smart, but like.
Hey.
Yeah, we're the ones that haven't lost the
All right. So what you guys are gonna do? All right. We're gonna do this activity. All right. About forces. All right.
Maybe second period feels bad about themselves because they've lost riddles and we haven't, and so they want to do something that we can't do.
That could, you never know.
Like, what is second period? What is that, chemistry?
Physical science. Physical science. They're sneaky too.
Oh.
All right.
Imagine freshmen making you look for that cow number 3 for 40 minutes.
It's not that.
All right. So what you guys are gonna do? You guys are gonna be playing some tug of wars.
Wow.
Yeah. Oh. Oh. All right. Return. Can I put this guy over here?
No.
That would have been fun. All right. I'm gonna do the medium guy and a small guy versus big guy. Who do you think's gonna win?
It's gonna be the same.
Wait. I think it's moving.
Yeah, I was gonna say, I'm pretty sure we did.
Have you really?
Yeah, I forget one, but we definitely did that.
Okay. Well, you guys are gonna do this. You guys are gonna be pushing some fridges. All right.
Oh, yeah. It was a long time ago.
All right. You're gonna be analyzing different forces, answering the questions. All right. You guys can find this on the classwork tab. All right. There are a decent amount of questions. All right. It's on the classwork tab in Google Classroom. It's called Newton's Laws Inquiry-Based Lab. Okay. try this out. If you have questions, let me know. All right. Yes.
How did you come up with the name Jonathan?
Jonathan. I got to be honest with you. I did not. I did not.
Oh, it's kind of like
It's kind of like Rowlena.